Hello all and welcome back. So in this video, let's continue our discussion on asymptotic notations and learn about the big omega notation. So let's get started. Now coming to big omega notation, we say that this is the best case scenario. That is when we say that our algorithm for a given input, it's going to perform the best, right? This is actually what is known as big omega. So let's say if we have again a function which says that okay, how our algorithm is with respect to the input size, then the way omega is defined is omega of g of n when f of n, right? This time it's always be greater than c dot g of n. Like it can never take, we say that it can never take time lesser than this particular c dot g of n, right? Intuitively you can think that if you're let's say again the example best case scenario of Usain Bolt, that he says that hey, I can complete this 100 meter in 10 seconds, right? Absolute best. You like that's the exact definition of this particular omega, the best case scenario. Now again we can take any of these, like for example, let's say again if I take f of n is equals to if I take f of n is equals to 2n square plus n, okay, then I have to make sure that I'm taking the greatest lower bound. Okay, I'm taking the greatest lower bound, right? The reason for that is that, for example, you can take g of n here, which is equals to n log n or even some constant as well, right? And 2n square plus n is going to be greater than that. But that is not how we select our g of n. The way we will be selecting is we will be taking it n square, and for particular c value, now we have to make sure that we take this which is closest, right? So for that particular c, we can take c is equals to 2, and then we can say that hey, now this 2n square plus n is surely always gonna be greater than my 2n square, okay, and we can find the value of n as well, where n is going to be greater than or equal to 0. Of course, n should always be greater than or equal to 0. The reason for that is you will be having some input, right? That is how we are defining it. So again, if I try to explain this graphically to you, this is somewhere we will get a function, so pay attention. This is our graph, right? Let's say if this is my f of n, right, then my gn, g of n c is something like this. So after some particular point k, right, again after some particular point k where it can be greater, I am surely 100% sure that now my f of n is always going to be greater than c dot g of n. This point we can again say k, okay, so this k is always greater than 0 as well. This is the time and this is your n, right? So this is the mathematical way of defining it. I will actually ask you to just remember it as the best case scenario, right? So whenever we are talking about best case in terms of any algorithm, that is where we say that it is omega. These mathematical way I'm showing you so that you actually understand what is the exact way they have been defined and how they came into being, right? So again, for example, now let us also cover the last one, which is your theta notation. In your theta notation, again we just this time says that theta notation is the average case, okay, average case. So let's say for example, what it can be in your algorithm is when you say that finding the largest number, it is in the mid of your array, right? So it is the average case complexity, right? And mathematically again it can be actually be defined something like this. So when your f of n is there, it is c2 dot gn and some c1 dot gn, right? It is basically in between your lower and your upper bound. So this is what is known as average case. Runner example, you can always think that your runner is saying that hey, this 100 meters I can cover it at an average of some 2 minutes always, right? And in your overall example of a algorithm, if your middle, if let's say your largest number is at the middle of your array, right? So that is what average case time complexity is. Now to make a graph for this as well, we can draw it something like this. See, so we have, let's say, first f of n, which is something like this. and then I have something, the other two functions which are my C1gn, right? Let's say it is going like this, and similarly C2gn. Okay, just make sure that we are always aware that there should be some k post which it will be active, because for many small input it doesn't matter, right? Something which we have already seen. This is input. Let me write this is as C1 dot g of n. So your f of n will never be greater than C1 dot g of n, and it will never be smaller than C2 dot g of n, right? This is what I say as the theta. Okay, so this is the asymptotic notation theta. Now I hope all of them are clear. We have actually understood the same graphically, intuitively as well. Majorly we will be focusing on the big O notation. That is what, as I said before as well, is gonna get asked in the interview. Something you should always remember for many algorithms which you are gonna do in the next classes, and something which you will have to find when you now solve question going forward, right? So now when you solve the question, again you have to make sure of one thing very nicely, that you are finding the complexities of the algorithm which you are writing. I don't want you to be very hard on this as of now, that you are actually correcting them as well or something, but yes, I want to make sure that whenever you are writing some code, after this module particularly, you should have an idea, and you should always and always calculate the complexity of the code which you are writing. Okay, so great everyone. Now let's meet in the next video, where we are going to start with finding the complexities of our common algorithm which we have done, and we will then get a feel of exactly how the same can be done in an interview, exactly how you can do that without running the algorithm, even without many times writing the code as well, right? So cool then everyone, let's meet in the next video. Thank you.